In today's video, we're going to look at the basics of waves, including how to label the different parts, how to calculate the wave speed, and the differences between transverse and longitudinal waves. The first thing to understand about waves is that they transfer energy from one place to another, but they don't transfer any matter. So when light waves pass from a phone screen to your eye, or sound waves pass from the speakers to your ear, only energy is being transferred. Sometimes, though, we can interpret that energy as meaningful information, which is why our brain is able to build up images and tunes from the light and sound that it receives. To travel from one place to another, the waves vibrate or oscillate, as we can see in this displacement distance graph. The distance is how far the wave has travelled from the starting point, while the displacement is how far from the equilibrium point the wave has oscillated, so how far it's gone up or down. The maximum displacement is known as the amplitude, while the distance of one entire oscillation is called the wavelength. So that could be from equilibrium, up, down, and back up, or it could be from the very top of a wave, which we call the crest, down and back up to the next crest. It just has to be one entire oscillation. And the opposite of the crest is called the trough. Now, sometimes you might see a displacement time graph instead, which looks pretty much the same, but because we have time on the x-axis instead of distance, the length of one complete oscillation would be the time period instead of the wavelength. And the time period is just the time it takes for one complete oscillation. The benefit of knowing the time period is that we can then use this equation here to work out frequency, which is measured in hertz and is the number of complete oscillations per second. To see how it works, imagine that each oscillation takes 0.5 seconds. Or in other words, the time period is 0.5 seconds. This means that there must be a total of 2 oscillations per second. So the frequency is 2, which is what we'd get if we did 1 divided by the time period of 0.5. We can also use the equation the other way around. So time period equals 1 over frequency. So if we were told that the frequency of a wave was 4 Hz, which means 4 oscillations per second, then to find the time period, we'd just do 1 divided by 4, which tells us that each oscillation must be 0.25 seconds. The next equation to know is that we can find the speed of the wave, so the wave speed, by multiplying the wavelength by the frequency. So basically we multiply how long each wavelength is by how many there are per second, and that will give us the total distance they travel per second. To see how this works, let's imagine we had a sound wave that had a frequency of 400 Hz and a wavelength of 70 centimeters. What is its wave speed? Well, in this case, all we'd have to do is convert the 70 centimeters to 0.7 meters, because we always want our wavelength in meters, and then multiply it by the frequency of 400 Hz, which gives us 280 meters per second as our wave speed. The last thing we need to look at are the differences between transverse and longitudinal waves. In transverse waves, the oscillations are perpendicular to the direction of energy transfer, or the direction in which the wave is moving. Which is why on our drawing, the vibrations are going up and down, whilst the overall wave is travelling from left to right. Most waves we can think of are transverse, including all electromagnetic waves, like light and radio waves, ripples and waves in water, and the waves of strings like on a guitar. Longitudinal waves, on the other hand, have oscillations that are parallel to the direction of energy transfer. This one's a bit trickier to get your head around, but basically it leads to some regions that are more spread out, and other regions that are more compressed, because the wave's vibrating back and forth. In motion, it would look as if this area of compression is moving from the left to the right within the wave. Examples of longitudinal waves include sound waves and some types of shock waves, like seismic P waves. Anyway, that's everything for this video, so hope you found it useful, and we'll see you again soon.